Hello, this is Mrs. Schroeder. Welcome to Chapter 18. We're going to start talking about atomic nuclei and nuclear stability. We're going to talk about first describing what the strong force is, how it interacts with the nucleus. We're going to relate binding energy and nuclear mass defect, and we'll learn how to predict the stability also of a nucleus to find out when something might be radioactive and when it would be stable. So protons and neutrons make up a nucleus of an atom. We call these a special word now. We call it nucleons. A nucleon basically is any particle that is in the nucleus. The nuclide, another vocabulary term, make sure you have these written down, is a special term that we use to talk about a specific nucleus with a specific given number of protons and neutrons. So we can represent them in one of two ways. We can either talk about the element symbol with its atomic number and mass number. For example, the element symbol, its atomic number, and then its mass number. Or we can talk about the element's name followed by its mass number. For example, radium-228 is the mass number, or Einsteinium-253. We learned this term isotopes previously. They're atoms with the same atomic number, but they have different mass numbers. So same atomic number means the same number of protons, but the mass number is different, so the neutrons are different. So what does that look like when we have an isotope? When we write out which nuclide we're talking about, we could talk about tellurium as 122 over 52, 124 over 52, or 128 over 52. If you notice, we have the same atomic number, but we have different mass numbers. 122, 124, or 128, depending on how many neutrons it has. So if I have 52 protons in a nucleus, remember these are all positively charged things. We know that like repels like. Okay, so a positive charge should be repelling another positive charge. How is it that these 52 protons can remain in close contact with each other? And this puzzled scientists for a long time. And in 1935, this Japanese physicist, Hideki Yukawa, proposed that there's a force that holds them together. Simple as that. There's got to be a force in there that's stronger than this electrostatic repulsion, which is making them go apart. So this force has to be somewhere. And they came up with the very unique name of calling it a strong force, because it's got to be very strong. And they said all the protons and neutrons in a stable nucleus are held together by a strong force. The thing about strong force, it can only act over very short distances. Shorter distances than you can find in electrostatic repulsion. So in larger nucleuses, the nucleons are farther apart. So strong force might not work. So this is a small nucleus, and these are right next to each other. Strong force, if you look at the size of the arrows, they're very large. They're bigger than the electrostatic forces, and they're holding it together. As the nucleus gets bigger, you see this right here is getting bigger. They're getting farther apart. As they get farther apart, if I look at the size of my arrows, my strong force is getting weaker. And if I were to move these even farther apart, let's say I took this one and I were to move it out here because I had an even bigger nucleus. Now these strong forces would be so tiny that electrostatic repulsion would basically just blow apart the nucleus. It would break apart because the strong force would not be stronger than electrostatic repulsion anymore. Now, have you ever heard the term quarks? We didn't stop at the knowledge of electrons, protons, and neutrons. We stopped there first semester because that's as far as we had time to talk about. But scientists have discovered this thing called quarks. They found out that electrons, protons, and neutrons are actually made of even smaller things. And they came up with the term quark. They first identified them using the high-energy nuclear collisions you'd find in the cyclotrons and synchrotrons, like Fermilab. they've identified 6 types of quarks, and they call each type a flavor for some reason. So the 6 you have are up, down, top, bottom, strange, and charm. Those are the quarks. I'm not sure why they call it strange, and charm. They ran out of names, I guess, for directions. But the quarks will make up the protons, neutrons, and electrons. And we know now that a proton is made up of 2 up quarks and 1 down quark, while a neutron is made up of 1 up quark and 2 down quarks. So they know how these are made up. Now we also know that in chemistry we've talked about several times what makes a system more stable. Systems become more stable when they release energy. It goes same back to our chemical reactions we've had. We're always looking for a negative delta H. We want it to become more stable, lower energy state. This applies also to things like nuclear reactions. We know that if you had a proton floating around in space, it's not very stable until it reaches something else and can react to form a nucleus, which is more stable. If 2 protons ran into each other, you'd have to have a more stable state for them to stay together. So we actually get to a lower energy state in order to make them more stable. Separate nucleons, when they form a nucleus, they give off energy. There's a tremendous amount of energy released in this reaction compared to chemical reactions. Much, much more energy than what's in a chemical bond. When these energy comes together, we call this the nuclear binding energy. That's the energy that's released right here. This energy. So where does it come from? This is where Einstein comes in. You've probably all heard Einstein's theory, equals mc squared. Probably never knew what it meant. But yes, energy can be changed into mass, and mass can be changed into energy. And we're going to learn how to relate this to each other. And he's talking about things at an atomic level. This is not going to be like your chair is going to turn into energy magically. This is more of an atomic level when I have nucleons forming different nucleuses. And what he found, the reason that Einstein came up with this theory, is that he found that the mass of the nucleus is less than the mass of individual protons and neutrons. So let me say that again. If you take 2 protons and you put them together, and you know what the mass of each one is, once you put them together, there's less mass. Everything we've done up to now is said you cannot create or destroy matter. Well, yes, you really can. And only in these nuclear reactions where we have energy converted to mass times the speed of light, times c squared. And the speed of light is this number, 3.0 times 10 to the negative 10 to the 8th meters per second. I'm going to show you how to calculate binding energy. I want you to write this down. Write down the steps, and I'll show you how to do this in class tomorrow. Make sure you write down these also. The mass of a proton, the mass of a neutron, and the conversion of an AMU to a kilogram. In order to calculate binding energy, I first calculate mass. Second, I take the mass defect and I convert it to kilograms. And then I use E equals mc squared to convert this mass to energy. So I can actually calculate how strong that energy is that binds the nucleus. And again, things that have stronger energy binding them together, this again relates to our chemical reactions. Is the same analogy as if it's got very, very strong bonds, like ionic bonds, it takes a lot of energy to make them break, to melt them. Same idea with nuclear binding energy. If I have a lot of energy released, I have very strong bonds. If I want to break that nucleus back apart, it takes a lot of energy. So more energy that's given off becomes more stable. We'll talk tomorrow in class. We'll show you how to actually calculate binding energy. We'll talk more about stability of atoms or of nucleuses, and we'll talk about how to calculate the stability and compare stability of different nucleuses based on binding energy and also based on ratios. So tomorrow in class we're going to continue this discussion. Be prepared with these things written down in your notes.